All right, so we're trying the electricity and magnetism video lecture here again. This is going to try to hopefully end up on YouTube, so we'll see. All right. Sorry about it if it didn't work for you on that Zoom or on the Loom link, but here we go. So I'm actually going to start a little bit about some history here. And I know I'm not a history teacher, but I'm going to do my best, basically. There's a lot you can learn from the history of science and how we do it. I mean, the history of science is still unfolding, basically. We're going to come back later, I know, in the next few years, at least in the next decade or so, and look at how science is dealing with this worldwide plague, basically, and how we studied it, and how we measured things, and how we came up with a vaccine and all that. That's going to be part of what some of the kids in the future will be learning here, and you guys are living through it, basically. So anyway, so a little history about electricity and science. Here we go. We're going to go all the way back to cave people. Okay, not talk too much about them. They didn't leave much of a written history. That's why it's called prehistoric. But they knew about shocking stuff. I mean, if electricity is just moving electrons, then that happens. That's static electricity, which we're going to talk about next week, is a good example of that. Not very useful, kind of dangerous at times. So, but that's sort of the start. Matter of fact, we're going to actually start in the 1700s with people like nobody other than Ben Franklin. And, well, what would become the United States. We were just the colonies then, but we were about ready to become the United States there, basically. So, yep, that's showing up pretty well. All right. And he did all kinds of static electricity charts. Isn't he famous for going out and flying his kite in a thunderstorm and realizing that, hey, lightning is another just big example of the same thing they were doing? If you want to do some extra credit and you want to look up this thing called a Leyden jar, you can make your own out of plastic, aluminum foil, and some salt water, basically. And you don't charge it up with the electricity from the wall. You actually charge it up by doing the little friction stuff that we're going to look at with static next week. But it's kind of cool. Be careful. I mean, you could get a pretty good shock out of it, but it's just a lot of fun. So really, that's sort of the beginning. You know, people were looking at this and trying to figure out what this phenomena is. What should we call this? Actually, Benjamin Franklin had coined the two opposite charge names that we still use today, positive and negative, just with those two words. But hey, we're going to go to about the 1780s, a little bit here, and a guy, one of my favorite names in the world of science, Luigi Galvani. Sounds Italian, doesn't it? And you'd be right. Was doing a cool experiment with dissecting frogs. He wanted to know about the anatomy of organisms. He was looking at a frog leg, for example, muscles, bones, blood vessels, nerve endings, and things like that. And you're thinking, what has that got to do with electricity and magnetism? Well, interesting connection. He noticed that every once in a while he would do something in his frog leg, which was freshly killed, not preserved like some of the students' frogs that you guys dissect, which are nice and stiff. But this loose and freshly killed frog leg sometimes would twitch. Right? It's like the muscle was alive almost, but it obviously had energy and it could move. He noticed that it only happened when there was a piece of iron attached to it, and then he used a little brass hook to do that. He wasn't interested in the physics behind all this or the chemistry necessarily. He was looking at anatomy, so he just sort of shared that idea with some friends. And one of the guys he talked to about was a gentleman who let me write that a little darker here. About 1800 was the year. See if I can spell the name right. Alessandro Volta. And he lived in Italy also. He was actually a count, just kind of cool, kind of famous and rich, basically. But he took the idea that it was these two different metals that created this electric current, basically, that allowed the muscle to be shocked. People didn't really understand that whole phenomenon yet, but they kind of knew that electricity, could make your muscles twitch a little bit there, even if you were alive, and even for a dead frog there too a little bit. So he started studying different types of metals, and the metals themselves weren't just enough. He needed some sort of solution, if you will, for them to react with. It turns out that body solution is not pure liquid. It's not, water is important for our body, but the salts that are dissolved in the water are also very important. Turns out that our body tissue is very much similar to ocean water, basically, for the amount of salt and the type of salt that's in it there. So that's an interesting little tidbit there. But anyway, so he actually is given credit for producing the first battery. He used silver and zinc and some salt water, basically, to produce a current, all right? Instead of just building up electrons and them jumping wildly in bunches, you could get this nice, smooth, constant flow of electrons, generally through a wire. Does that sound familiar? Yeah, that's what we've been studying for the last week or so. We would call it current electricity. So this is a huge thing. I want to try to show you that. Here, I got a little setup here, so follow along with me here. And let's see what we got here. Anyway, so I've got some metals, and unlike the Count, I don't have silver or, well, I got zinc right here, but I have copper instead, so can't afford the silver like Mr. Volta had. I'm going to hook them up and try to make electrons flow through a circuit. Sounds like fun. All right. This is a lab we would do in class if we had a normal class time here. So if you notice, so what do I got here? I've got some wires. I need to move back just a little bit so you can see what's going on. I got a circuit that involves the two different metals, and then they flow through a meter. In this case, the meter is measuring, is measuring something that starts with an A. I wonder what that could be. What do we measure that starts with an A in the world of electricity? Amps, you are correct. All right, so let's touch these two together and see if we get any amps. What? I'm getting no amps. If you notice a little red part on my meter there, 0 amps. That's no good. All right, so I need something. I have just a little beaker of water here, and let's just see what good old tap water does. Remember, tap water is not pure. It's got some minerals in it. So, hey, we get a little bit of a volts there. And it's going to the negative side. We'll worry about that a little bit later there. So I'm going to go ahead and do what Mr. Volta did. Add a little bit of salt to my water here. Pretty easy to make some salt water. Let's stir it up. Stir, stir, stir. And now we'll put it in there. Ooh, we get it a lot more. We can go all the way to the bottom if I stir it up really good. All right. So that's allowing, guys, hey, that needle moving indicates that electrons are flowing through this wire. And before you freak out a little bit and think, whoa, Mr. Dick made 500 amps of electricity with just 2 little pieces of metal, and you remember that, less than 1 amp could seriously hurt you, right? Could even stop your heart. In your house, the big ticket items like an oven or an air conditioner run on about 30 amps. And here we are making 500 amps? Well, no, not quite. That little funny looking symbol there is a Greek symbol, and it stands for micro, which turns these into microamps, which only makes them 1,000,000 times smaller. So we're making 500 millionths of an amp, or maybe 1,000, making about a thousandth of an amp here. So very little current is flowing here, but we're getting them to move there, right? And this is the start. So now scientists know how to make electrons move through a wire, basically. What could we do with that, you ask? Hold on here. Let me show you something real fast. If the negative part is messing with you, I'm going to just reverse. I'm going to put the red wire on the copper. This is backwards from what I just had. And the green on the zinc. And let's see what she does. Oh, yay. It's just the same amount of voltage, but it's on the positive side. So in this case, the ammeter here shows us, actually this is called a galvanometer. Ooh, I wonder who they named a galvanometer after. Luigi, you think? Ha, good answer. All right. So the galvanometer measures microamps, and it shows you which way they're flowing. Are they flowing in this way? Then they're positive. If they're flowing this way, then they show up negative on the amp there. So remember, that's a type of direct current here. So, all right. So now we've got electricity. Let's involve some magnets with it. How about that? Because that's the whole idea. Electricity and magnets, best buddies, best friends, go everywhere together. All right. So, all right, erasing those names. Now let's scroll down a little bit. And let's see what we got here. All right. So, all right. So now where are we at? We're in the 1800s now, about the 1820s. All right. And a gentleman by Hans He has a big name. Hans Christian. Oh, oops, can't spell his last name. Oerstd, I believe. Gentleman lived in Denmark. Pretty cool little country there in Europe. Was a physics professor, right? And by now, people were making batteries all the time. Volta's idea got spread. You know, scientists talk to each other all the time. He was showing them how you can run these currents, you can make this battery, and you can do this stuff. Like at the time, they weren't too sure what are we going to do with this. We don't know. It may fade out and not be very important, or who knows? It might be kind of a big deal, as we say. So he just happened to have a little compass sitting near here, and if you realize a compass is a magnet itself, all right? The compass needle is a magnet, and it is influenced by the Earth's magnetic field, which always runs north and south. Therefore, that little compass needle likes to point north and south, basically. All right? So, here, let me show you kind of a quick example of what he did here. I'll come back to my little demo table, if I can make this work. So, what do we got here? So, we got a little compass needle in the middle here, and you can't see the needle is sort of going along with these little wires. So, I wrap the wires around there to make it a little bit more obvious here. But so, what I have then is I've got a battery here, all right, and I'm going to complete the circuit. I'm going to hook up the little black wire here, so the electrons are actually going to flow through the wire, all right. And if you notice, so right now I've got no electricity. Let's go ahead and get my little. I just have to touch it over here. Complete the circuit. Remember one of our rules. All right. And let's check out the compass when this happens. Whoop. Oh, dear. What did the compass needle do while we did that? Boom. So when electricity, here, watch. I'm touching electricity. No electricity. The electricity influences the compass, just like a magnet would. Basically, I'm using a current of electricity to make a magnetic field. Ha! That is a huge discovery right there. This is big, guys. All right. I'm going to go ahead and switch the wires on the battery here and make the electrons flow in the opposite direction, just like we did a little bit earlier there. And let's see what the compass does. If you're paying attention, you'll notice that now the compass goes in the exact opposite direction. The red needle is kind of pointing to the left instead of the right there. So, which brings up a very important thing that if we could flip-flop the current of the electricity, I could get the compass needle to go this way, and then this way, then this way, then this way. I could get that compass needle to spin. You know what kind of invention we're talking about here? When you use electricity to make something spin? I'm thinking motors, and you would be correct. Super duper. All right. So, thank you, Mr. Oersted, for discovering that. So basically, we're at the point where, hey, we can make current electricity. We can make electrons flow nice and smoothly, doing it chemically with metal electrodes and then like an electrolyte, like an acid or salt water or something like that. It turns out that current of electricity, when you make it flow through a wire, it's producing a magnetic field. And if you wrap the wires around in a circle, you can intensify that magnetic field and make the magnetic field pretty strong, actually. So the next step might be, if we can turn electricity into a magnet, can we turn a magnet into electricity? So I believe the year was 1832, perhaps. Two guys at the same time. Joseph Henry, who happened to be a good old American, and now we are the States, and, oops, how you spell Michael? Michael Faraday in England. Did just the opposite. They took a magnetic field, if you will, and they used that to get electricity moving. So instead of like Volta, where he was using chemistry, using chemical energy between the metal electrodes and the liquid electrolyte to push the electrons, here we didn't mess with anything. We just used a magnet, basically. So I can show you that. Here, let's check this out. All right, so coming on over here. Gonna go back to the old galvanometer. All right, and so one more time. So instead of doing some chemistry to make the needle move there, all right, because chemistry is going to run out after a while. These things are changing when they're in the salt water, and they're not going to stay the same chemical formula over time, basically. I'm just going to take a big loop of the same kind of wire. This is just copper wire, and I'm going to hook it onto one end of my wire, and watch what happens when I hook it onto the other end. Are we checking this out? It's going to be amazing. And boom! What do you see? What? Nothing? Well, that's because a wire by itself isn't going to produce any electricity, right? We have to do, some chemistry like in the world of a battery. Hold on, I got to go get something. I'm coming back. Or we're going to use a magnet this time. I went and got my big honking neodymium magnet. This one's pretty powerful. And, whoops, I'm just going to, let's see the meter there. I'm going to put it inside the coil of wire here, and let's see what happens. What do you notice? Well, it wiggled a little bit, but if I don't move the magnet, I don't get any current. But if I do move the magnet, aha, look what I get. I get the needle to move. Yay, I'm making electrons flow through the wires. Cool. With basically just spinning a magnet. Remember, so if the magnet sits still, that's not good enough. I got to move the magnet, all right? And if you notice, which way is the needle pointing? It's going to the left, it's going to the right. I need a word for that. It's not staying in the same place. It's going forth and back, in and out, left and right. Got an A word you can think of here? What kind of electricity are we producing with this spinning generator magnet? 1, 2, 3. Alternating electricity. You got it. Alternating current. We call that AC. So if you notice, batteries make the DC. It goes in one direction and stays there. Spinning magnets make AC. And by the way, I could hold the magnet still and spin the wires, if I wanted to. All right, and I get the same current there. So this was all the early 1800s. Now we've got other ways to make electricity. Basically, we can use chemistry with batteries, or we can use just spinning a magnet with a generator, is what they ended up calling that. And all kinds of cool stuff could happen because of that. So, hey, let's just wrap up the notes here real fast. Here we go. All right. And just summarize this. So the idea, the phenomenon of electromagnetism is pretty basic, pretty simple. And here we go. Rules of electromagnetism. Uh-oh, what is that? Go away. And electric current. Oops. Supposed to be the letter C. Yeah. Electric current, aka moving electrons, makes a magnet, all right? And let's just flip-flop it. A magnetic field. A magnetic field moving relative to a wire produces an electric current in that wire. Hey, that's pretty cool, right? In other words, electricity makes magnets. Magnets make electricity. That's the short and simple way of doing it, all right? Personally, I would have called that phenomenon magnoelectricity. What do you think? Give the magnets the top billing there, but I don't know. Somebody went with electromagnetism. They probably had a better publicist or something, and electricity got the top bill in there. So, all right. Hey, I'm going to just show you what this can be used for here. So, uses of, oops, let me erase the words. I'm sure you got the words down. If not, pause it. 3, 2, 1. All right. Okay. So, this is what the generator, that's what Joseph Henry and Michael Faraday came up with. Let's use mechanical energy of a spinning magnet to push electrons through a wire, okay? If we flip-flop it and do what Oersted did, we can turn the electricity back into magnetism. It can attract and repel something and make it spin. Oh goodness, we got all kinds of things. Motors do the work for us, all right? People work, but they don't physically work like the good old days. I mean, motors are it, man. Yeah, and gasoline motors do a little bit, but every day more and more we're switching over to electric motors, right? And then down here where it says other devices, all kinds of good stuff here. So I should actually scroll down a little bit here, see if you can get this. If you need to pause it, do it now. Here, I'll do pause. Okay, I really wasn't paused. I was just faking it there. All right. Motors, all kinds of motors. There's way more motors than this. And finally, other devices. So, crazy, crazy stuff here. All right, don't turn it off yet. Hold on, let me go and I can show you a little generator here real fast. How much time? Oh, we've only been 20 minutes. Shoot, this is nothing. All right, so what we got here is a generator. All right, it's a coil of wire and a magnet basically, and this is one long wire. It goes around. You can't see it. It makes connections. Whoops, over here. And then they go down and inside to here, and they go through a little LED, then they go all the way back. It's one continuous loop. If you remember, one of our rules of electricity has to be that. So if I give the old generator a spin, you should be able to see my little LED lighting up. Woohoo! Hey, that's because the wires are going through these magnetic field lines in here. Your textbook will tell you about magnetic field lines. And if you come to class, we'll take a look at them too. Let's get rid of the magnetic field lines and give it a spin. Hey, the LED's not coming on. What happened? Well, the only way you're going to push the electrons through the wire is if there's a magnetic field making it happen there. So, haha. All right. Let's reverse this idea. Because really, what we got here is a coil of wire and a magnet. What do I have here? I've got a coil of wire and a couple of magnets, but it's the same basic idea, but I'm just going to do it in reverse. I'm going to put the electricity in with a battery here. This is from one of my tools, all right? And I'm going to get it to move. So instead of mechanical into electrical as the generator does, I'm going to start with electrical and then end with some mechanical. See if I can get this little spindle in the middle, the axle, to just spin. Hey, notice it doesn't touch anything. What is causing it to move if it doesn't touch? All right, don't mess with me. Yeehaw! I love that, basically. So every motor basically works this way. This thing becomes an electromagnet, all right? And it either attracts or repels to the other magnets on the side. If you're watching really close, we're switching the direction of the current on top here every half a turn, which makes this go, we flip the polarity. Whoop, north-south, south-north, north-south, north-south, north-south. You know what I'm trying to say, right? So attract, repel, spin, 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 spin. All the while, nothing really touches each other, acting at a distance. Electric motors can be incredibly powerful. This little guy isn't going to do much. It might sharpen your pencil, but, I mean, electric motors move trains, all right? You see a train with 100 cars behind it fully loaded. Those are electric motors inside those locomotives pulling and pushing and doing that. So that's pretty impressive. So, all right. And then, like I said, there's a few other devices that we can get to here. Speakers use electromagnets, all kinds of good stuff here. You can store information on with magnetic here. This thing's a little solenoid switch. It opens and closes with an electromagnet. This is a pump on a dishwasher here. All right, I need to quit talking. So, here we go. You got a whole bunch of lists there. So, like I said, electricity itself, kind of a big deal. When you throw magnetism in it with it, man, it just magnifies it and makes it so much more bigger and so much more powerful. So, all right, hopefully I can get this on YouTube and you guys are watching me, and then I'll apologize for any issues or problems that you had. So let's get out of here. Good luck.